Hello everyone, this is Ahmed Al-Halek. This video is about creating a Cloud9 SSH environment. Now, if you went to your Cloud9 dashboard and clicked on that orange button for creating an environment, you would see one of two options here that you should pick in order to get your environment type. Now, the first one is saying create a new instance for the environment. This basically means that this environment needs a server to run, and this server is existing on the virtual machine. If you don't have a virtual machine or an EC2 instance per se, you would need to create one in order for it to host your environment for you. I have two main problems with the first option here, which is creating an instance especially for your environment to run on. Now let's address the first problem, which is related to the EBS size, the EBS volume that's going to be attached to this instance that's going to be created on the spot. Now, if you have created an account on AWS and you're enjoying your 12 months of free trial, then you would most probably go to the free tier eligible T2 micro as an EC2 instance type, which comes with 1 GB of RAM and 1 virtual core, which is actually pretty good for exploration and like figuring what this instance can do and what it cannot do with this specs, with this given specs. But whenever stuff gets a little bit heavy, like for example, if you have installed something like Nginx or any web server and try to host it any kind of website, using this T2 micro, stuff is going to be a little bit sluggish with you. Things are going to be heavy on the terminal. You can't use your normal commands normally anymore because everything is heavy on the system. Anyways, if you are in your 12 months period of free trial, then you would most probably go with the T2 micro EC2 instance type. Now, what you should know is whenever you create an instance with the first option here, or sorry, whenever you create an environment with the first option, the instance that's going to be created on the spot to run your environment is going to be having an ABS volume of a default size of 10 GBs. Like whenever this instance is going to be spun up, immediately a storage of an ABS volume is going to be attached to this instance. And this default size of this volume or ABS volume is going to be 10 GBs. Now, in my case, this is something that is totally cost inefficient because in my case I have students, I have multiple members, and I want to create an environment for each member. Now if I created an environment for each one of them using this first option, then I would allocate an instance of a default size of 10 GBs for each one just to run their environments. This is cost inefficient to me for this reason. If you look the pricing on EBS volumes, you would know that if you attached an EBS volume of 10 GBs, you are actually being charged for the whole 10 GBs, whether you have allocated the whole 10 GBs or not. Okay, you are not charged for the amount of files that's going to be uploaded to this storage of 10 GBs. If it's the case of an ABS volume, then you would be charged for the whole 10 GB as the usage, whether you use them like totally or not, which is actually not the case when you use database on AWS, just for your information. So this is going to be a problem. I don't want to have every instance running a Cloud9 environment to be of default size of 10 GBs. If I can reduce this somehow beforehand, before the environment is even being hosted in the instance, then this would be great for me. So this is the first reason. The second reason is maybe in my case I want to create an instance and actually host multiple environments on the same instance. Let's say that I have multiple environments and I want these environments to be able to SSH into one instance. So to do this, the second option is obviously my solution. Now this second option is actually straightforward. There is nothing to go around and explain if you want to get things up and running as fast as possible and you can go to the documentation here on creating an SSH environment, and there's going to be an SSH host requirements that you should meet. And if you follow the documentation, everything is going to be really clear. But most of the time, most of the users who are not aware of some networking basics wouldn't understand what's going on or what's the deal with the protocols that's going to be set or attached in inbound rules or outbound rules into your ACL or security group. They're just gonna follow what's written in the documentation without actually understanding what's going on. And the same thing goes for the VPC, creating an IP address for the VPC, and or choosing an IP address for the VPC and creating subnets. All of these stuff you would find in the manual, you would find in the documentation, but most of the time you would just copy and paste without understanding what's going on. In my point of view, if you are responsible of some group of people and you want to provide them services, I think it's better if you understand everything to the fullest. Like, if you're the one in charge, if you're the one who's creating this environment and instances for them, you're like the manager of everything, you should understand why did you pick this IP address and how did you create these subnets, on what basis, and are these subnets correct or not. Of course AWS is going to tell you that's not correct if it wasn't correct, but you should understand these. If you have better understanding of these networking basis regarding the VPC and subnets and ACL, the internet protocols, the internet gateway, and the routing table, I think things may be a little bit clearer, and this is what I'm going to do in this video. So maybe the first 20 or 30 minutes of this video is going to be a quick tutorial on subnetting. You can skip this part and get to the part when I go to the AWS console and start creating a VPC and subnets. But if you want to understand what IP addresses or what private IPs that your instances are showing whenever you create a Cloud9 environment, and how actually did these IPs get there, maybe you would want to stick to this part. Okay, so I'm going to talk about subnetting, and I'm going to talk about how many subnets can we create based on two design cases that we're gonna have with some parameters and stuff. One of the two design cases is going to be the actual design case that we will implement whenever we go to the cloud, the AWS console, and start creating our VPC and subnet in this video. And I'm going to talk about subnets, how many subnets can we generate, how many IP addresses each subnet can have, and we're gonna list a little bit of detail about the IP addresses inside each subnet. Let's say like the first IP address, the last IP address, and the broadcast IP address of maybe a subnet or two. Alright, it's just like a way for us to predict the private IPs that's going to be showing up on the instances whenever we attach them or label them to be located under the subnets that we have created under this VPC. Okay, and whenever this is done, alright, we're gonna go to the AWS console and start creating a VPC, subnets, and internet gateways, and associate this internet gateway for the VPC and the subnets to make it public. And we are going to make or create the instance, configure it, give it an Amazon image, and configure the AWS volume, configure the security group. And whenever this is done, we're gonna SSH into it, and we're gonna install some tools and utilities that we're gonna need in order to let this instance able to host a Cloud9 environment via SSH. And finally, I'm going to revisit the security group after a while, after we have created the instance, and edit some stuff. And we're gonna build an optional ACL that can work as a common ground for most of the instances, or for most of the subnets that you're gonna create in your projects afterwards. Finally, we're gonna create a Cloud9 environment, and we are going to connect it to an instance via SSH. Now let's just recap this. Why do we need to connect via SSH? Just as I told you in the beginning, you get to customize a couple of stuff beforehand, especially then this is from my perspective: the volume, the number of volumes, the type of the volume, which is something that I'm going to talk about whenever we create the instance, and the size. And this is the most important thing to me, which we can reduce to the least minimum number. And we can actually configure the rest of stuff as well: VPC, subnets, internet gateways. And it's really good to have these things set up before the instance is created. Now, another thing that you might be interested in is that you can create multiple Cloud9 environment on the same instance if you are creating these instances via SSH. You can also have a synchronized workspaces. Let's say that you have a machine that you write your code on VS Code on that machine, and another place you are working on Cloud9 for some reason, and you would want to have your Cloud9 environment synchronized with your VS Code environment. You can do this if you are connecting via SSH. This is not going to be covered, by the way. The last point here is running your favorite IDE on the browser. Let's say that you have your favorite IDE to be Visual Studio Code. Now, to run Visual Studio Code on the browser, you would want to go to one of these two sites. The first one is basically Code Spaces, and this is pretty recent. I think this is released officially in like 3 or 4 months ago. So Code Spaces, which was previously called Online Visual Studio, is the service that Microsoft Azure, another cloud platform just like AWS, is offering you to be able to run Visual Studio Code on the browser on one of their instances that you create. But the catch here is that you should have a Microsoft Azure account. If you didn't want to use Code Spaces and you didn't want to have an account on Microsoft Azure, there is another service called Coder. Coder is basically just a platform that offers you to run VS Code in the browser. They let you run VS Code on their virtual machines. So it's the same thing. Eventually you would need to maybe create an account on their cloud platform and pay for their services. And now, if you are an AWS user, you would certainly know that AWS would never provide something by default for you to run VS Code on their servers, because like it's obviously not their product, it's Microsoft's. So you would want to have the distribution that Coder, for example, is using to run VS Code on their machines. You can find this distribution here on GitHub. It's called Code Server. Code Server is basically the distribution that you can use to host VS Code environment in your browser on whatever cloud platform that you use, whether it's Microsoft Azure, Google Cloud Platform, AWS, it's your choice. And since you are, if you're watching this video, then this means that you are an AWS user. We can host the VS Code on our instances that we can create on AWS. So yeah, you would want to go to Code Server on GitHub, get the latest release, and download this release on your machine, in your AWS instance, and then unzip the file, get to the binary that actually runs via Visual Studio Code in the browser, and just execute it. It should work, and it works by default in port 80. I'm going to have a separate video for it. So this actually sums up the points that you can use an SSH for. Okay, let's start our tutorial on subnetting, and please just keep in mind that this tutorial is a quick and a brief way for you to learn subnetting via practical examples. And hence we're gonna have these design cases where we will actually implement one of them on AWS when we actually get to create the VPC, the subnets of the VPC, the internet gateway, and so on. Okay, so just keep in mind that this tutorial will not obviously teach you everything about subnetting, subnet masks, and networking. Alright, it's just gonna give you a quick and easy way for subnetting if you have a practical example like ours. Okay, so let's get started. Now, any IP address consists of 4 octets, and each octet is actually 8 bits. Okay, so we have here an IP address. This IP address, for example, is following the classful form of an IP address, where the classful forms or the classful views were actually following one of these common classes A and B and C, and these classful forms or classful IP addresses were being used like maybe a decade or so ago, I don't remember, but it's not used anymore. And the only IP addresses, forms or views that is being used nowadays is the classless IP address. Now, what is the difference between a classful IP address and a classless one? Obviously the / and the prefix that we see here. So whenever you see an IP address like this is following one of the traditional classes, which is not actually being used anymore. And this is a classless IP address. You know one is classless whenever you see this prefix at the end. Okay? Now an IP address, as I told you, any IP address consists of 4 octets. Each octet is 8 bits, which yields by the end a 32 bits. So an IP address actually consists of 32 bits. These 32 bits are divided into network bits and host bits, meaning that they are divided into bits that are reserved for the network, and there are bits that are reserved for the hosts, which are the clients or the users that's going to be on the network. Okay, after subnetting, we're gonna have another category popping up, which is the S bits or the subnetting bits. All right, so let's go back to the classless view that we have here. The classless view, or the sitter notation, which is the classless interdomain routing, I'm just gonna call it the classless view for short. This is how it looks like, and this prefix that we have here actually corresponds to the network length, meaning that these 24 means that we have a 24 bits, which actually corresponds to 3 octets that is reserved for the network, hence it's actually representing the network length. Right? So whenever you have a 24, for example, you know that the first 3 bits, the first 3 octets, which actually corresponds to 24 bits, is the network bits number. Okay? So looking at this IP address, we have a network bits of 24. And we have the rest of the bits, which is the last octet here, is the 8 bits reserved for the hosts. It is also really important to understand, is that a subnet IP address or is it not? Now, you can determine this by looking at the prefix here. Okay, whenever you have the prefix as 24, this means that the network bits is going to be the first 3 octets, hence 24 bits, right? And if you see the host bits having zeros in the last octet or in the last 8 bits, then this means that there is no subnetting happened here. There hasn't been subnetting done on this IP address yet, okay, since it follows the default subnet mask. And the default masks, for example, the common classes of the classful IP addresses, which are A and B and C. If we take, for example, class C to start with, we would see that class C has a number of n bits that is equivalent to 24 bits, which is exactly this. It's the same case of this classless IP address, right? So having a prefix of 24 means that there are 24 bits, and this makes the default subnet mask looking like this. Okay, if we took the case of class B, you would see that class B has a network bits of 16 bits. Yeah, so you would see the prefix of a classless IP address that actually looks like a class B IP address of having 16-bit in the prefix, which actually would make this 1 to be a 0, meaning that the first 2 octets, which is actually 16 bits, are the network bits, and the next 2 octets are the 16 bits for the host bits, right? So if you saw something like this, this prefix evaluates to this default subnet mask 255.255.0.0. And finally, if you had a class A that actually has an m bits of 8 bits, you would see its prefix or the network length be written here using the same exact fashion, and you would see it looking like something like this, just to represent that the first octet is what's actually being reserved for the network bits, and the last 3 octets are actually being prepared or reserved for the host bits, which corresponds to 24 4 bits, right? So a subnet mask of a prefix that looks like this would be just allocating the first octet to the fullest, which is going to be 255,000. Now let's just get this back to how it normally looked. Okay, so this is our original IP address that we're gonna find ourselves working with in this first design case when we get to subnetting right now. But just keep in mind that I'm just giving you a brief talk about subnet mask. I'm not going to go into deeper details about what if we had a prefix like this or this that doesn't actually follows the default subnet masks. You can actually search for this, but instead I'm going to jump into directly a practical example on how can we learn subnetting within a design case. So to understand subnetting, it's better if we had a practical design case. So for example, let's take this group right here. Let's say that we have a group of 28 members or 28 students. Each one of them should have his own or her own machine with its dedicated IP address eventually. And let's say that we are given this network's IP address, all right? Or let's say that we have chosen this IP address, whatever. Okay, now this IP address is the one that we have been discussing so far. This is a classless IP address or a set notation IP address. It follows the looks of class C, if you remember what we have been saying earlier, since you can say that you can see that this IP address actually has a 24 bits reserved for the networks, which is actually the deal here with class C. As you can see, there is 24 bits reserved for the network. Anyways, a good starting point will always be to look at the traditional classes, which is class A and class B and class C, and ask yourself what class actually provides the least number of host addresses. And I've said the least for a specific reason. We would want to minimize the number of wasted IPs. Eventually, there will be wasted IPs. So it's better if we minimize the number of wasted IPs. But for a starting point and for a common ground, let's just look at the traditional classes and let's see what classes of these three would give us the least number of bits that can be reserved for hosts. And the answer is obviously class C. It gives you the least number of bits comparing it with B and A. It gives you an 8 bits for the hosts. So within this choice that we made, like we chose here class C, and obviously the classless IP address actually looks a lot like class C since the prefix here. But anyways, let's say that we have chosen class C, which actually provides you with 8 bits for the host, which is basically the least number of hosts that we have in this traditional classes table. Let's take the 8 bits for the hosts and plug it in this formula, which is 2 to the power of h minus 2. And I'm going to tell you what this 2 deduction actually corresponds to. But we would want, based on our choice, calculate the number of hosts that we would get if we had a number of bits of 8 bits reserved for the hosts. So you would have 2 to the power of 8, which is 256 minus 2 gives you 254 addresses. So if you chose class C, you would have a total number of 254 addresses. Now you should actually calculate the wasted IPs. So let's say that we need only, just as we discussed earlier, 28 students, or I'm sorry, 28 IP addresses for 28 students or 28 members. So 28 IP addresses deducted from the whole number that an 8-bit reserved for the host actually provided by class C, it will give you a wasted number of IP addresses that is equivalent to 226, which is actually a lot, which is going eventually to be cost inefficient for you. So instead of fixating ourselves on one of the traditional classes to use, we can actually tweak this equation a little bit in order to get the desired number of host bits. We can simply do this by replacing the equal sign to greater than or equal, and on the right hand side we're gonna put our desired number of individuals or the desired number of IP addresses that we would want to at least have anything that equivalent to this or even larger, and our variable of the equation is going to be the power here, which is going to be the host bits, right? Now I have listed on the right hand side some terms, I believe the first 11 terms from the geometric sequence that's actually following the formula of 2 to the power of n. And if you're wondering why did I use 2 to the power of n, is basically because in the binary numbering system the base is 2, okay? So you would see 2 to the power of 0, 2 to the power of 1, 2 to the power of 2 for the third term, 2 to the power of 3 to the fourth term, and etc. The same thing goes if you looked up the hexadecimal binary, the hexadecimal numbering system, where you would find the base 16 to the power of 0, 16 to the power of 1, and etc. So coming back to this, on the right hand side you would see the geometric sequence starting from the power of 0 until the power of 10. Now ask yourself, what term of these terms can actually get you to cover the number of IP addresses that you would want to have? The answer here is obviously 32. 32, which is basically 2 to the power of 5, is the number of IP addresses that will give you at least 28 addresses. So we will plug, instead of this h here variable, we're gonna plug 5, and 5 we're gonna work for us as the host bits, and this will eventually is going to be 32 minus 2, and there's gonna be 2 IBs that's going to be deducted from the 30 IBs that this number of host bits is going to provide to you. And these 2 IBs are the broadcast IP and the subnet IP address, and I'm going to mention this at the end when we actually create the subnets. Okay, so by the end of the day we're gonna have 30 IBs if we chose the host bits to be 5. So our solution, or our common ground or starting point, is going to be having the host bits to be 5 bits. Okay, that's the start of everything. Now just remember, that's just a reminder that we have this IP address. So what is next? Remember what I told you earlier about the IP address that is actually consisting of 32 bits, which is divided to 2 categories before subnetting, which is the n bits followed by the h bits, or the host bits. After subnetting, or while subnetting, you're gonna have a third category in the middle, which is basically going to be the subnetting bits. Now since we decided that the number of host bits that will be allocated into the last octet here is going to be 5, we are going to start subnetting this IP address. We're going to create multiple subnets or subnetworks from this IP address. Now notice here that this classless IP address gives you by default a 24 bits for the network, and hence the first 3 octets are already reserved. We can't do anything about it, but the only octet that is left to us, which is the host bits, or the last octet, or the last 8 bits here, this is what we will configure both our subnetting bits and the host bits. Now I have actually made 8 columns here. Okay, these are 8 columns. Each column represent 1 bit, since the last octet is basically 8 bits. So these 8 columns or 8 bits represent the last column as a whole, or I'm sorry, the last octet as a whole, which is represented by 0 here. Alright, and I have used the same geometric sequence that I have used in these terms above each bit of these. So let's say that we starting our bit this. So this is the first bit, the second bit, the third bit, up until the last or 8 bit. And let's say that the first bit is going to have the formula of the geometric sequence to be 2 to the power of 0. Alright, we start counting from 0, so the power is going to be 0, just as this one. So 2 to the power of 0, this is going to give you 1, and the second bit is going to have 2 to the power of 1, which is going to give you 2, and the third bit is going to have 2 to the power of 2, which is going to be 4. The fourth bit is going to have 2 to the power of 3, which is 8, and etc. Okay, and we're gonna have by the end 2 to the power of 7, because we have started the counting or the power from 0. Alright, so again, just to recap, these 8 columns represent each one of the 8 bits in the last octet, which is the only thing available for us in this IP address in order to modify and configure regarding the subnetting bits and the host bits. Now, since we have actually calculated the host bits needed in our design case to get our 28 individuals their own IP addresses, we can start populating the host bits. So we have a number of host bits equivalent to 5 bits, right? So let's pick our first 5 bits in this octet, in this last octet here, and this just fill it with labels just to know that each one of these 5 bits correspond to an H bit. Okay, remember what I told you earlier here when I said that the host bits are going to be assigned to zeros and the network bits are going to be assigned to ones. Now this is what's going to happen here now. So we have decided that the host bits are going to be 5, and we assign the first 5 bits to be host bits. What is left for us is going to be the subnetting bits, and this is where the subnetting is actually going to take place. Okay, so the left bits of the octet are only 3, so we end up with 3 subnetting bits. Right, so we have 3 subnetting bits. Okay, the moment that you figure out the number of subnetting bits that you have is actually a good point for you to calculate the number of subnets that you would eventually have by the end of the day. So in order to know the number of subnets, you're gonna use the same formula that we have used earlier, which is the geometric sequence, 2 to the power of s. Okay, and since s here we have 3 subnetting bits, so s is going to be plugged as 3 since we have 3 subnetting bits. So 2 to the power of 3 is going to give you 8, and this means that we are going to be able to create 8 subnetworks of this given IP address. Alright, so we're going to have 8 subnetworks, alright, 8 rows or 8 subnetworks out of this IP address. Before creating the 8 rows that corresponds to the 8 subnetworks or the 8 subnets, we just need to modify the prefix here now. Remember when I told you that after subnetting our IP address, we're gonna end up having another category in the middle, which is the subnetting bits. Yeah. Now the prefix, which is the network length, is determined using the network bits plus the subnetting bits if you're ever using subnetting. Okay, so in this case the prefix for the new subnet IP addresses will change. It's not going to be the same as 24, because when it was 24 it was only 3 octets, 24 bits for the network, but now the network length will going to be the network length, the network bits, which is 24 bits, plus the subnetting bits, which are 3 bits. So having a network bits of 24, just as the prefix say, plus the subnetting bits gives you 27 of a network length. Alright, so 24 plus 3 gives you 27. So this is the new prefix of our subnets IP addresses. Now I'm just gonna pause the video and create 8 entries or 8 rows, and each row actually correspond to a subnet, and I'm going to tell you how we are going to fill the values for the host bits and the values for the subnetting bits. So I have created here the 8 rows, which actually corresponds to the 8 subnets that we have just calculated here. Now what is left is to give values for the host bits in each row or in each subnet, and to give values for the subnetting bits also as well in each row or in each subnet. Now I told you that the host bits are going to be assigned zeros, right? But what are the values that the subnetting bits are going to take? Now let's first populate this mini table that we have here that actually consists of 3 columns, which are the 3 subnets or the 3 subnetting bits. Okay, so the way to do this is that you go to the first column, the first subnetting column on the right, and you do 0 1 0 1 0 1 0 1. Then you go to the next column or the second column, and you put or you write doubles of each. Okay, so 0 0 1 1 0 0 1 1, and you go to the third subnetting bit column and you put quadruples of each. So we're gonna have 4 zeros and 4 ones. If you're wondering how did I know this, it's simply following this same geometric sequence that we have used to represent each bit, where we say the first bit is 2 to the power of 0 and the second bit is 2 to the power of 1. It's the same thing. So here the first subnetting bit column will be 0 and 1, 0 and 1, which is following the sequence 2 to the power of 0, which is going to give you 1. The second column, which is doubles of each binary number or binary digit, is going to be following the next term in the geometric sequence, which is 2 to the power of 1. Okay, so 2 to the power of 1 is going to get you 2 or doubles of each. The third column is going to be quadruple of each, hence the third term here, which is 2 to the power of 2, which gives you 4, right? So quadruples of each binary digit. Okay, so if we had a fourth column or a fourth subnetting bit right here, so this column, I think you guessed it right now, the fourth column is going to follow 2 to the power of 3, which is going to be 8. Okay, so you're gonna have octables, 8 zeros followed by 8 ones, etc. Okay, now after populating the subnetting table, the easiest part left is to populate the edge bits or the host bits for each subnet of these 8 subnets. Alright, as I told you, the host bits by default gets assigned zeros, so I'm just going to fill zeros for each subnet like this. Okay, and this is done. Remember, this first row here is just the header. This is just the header of the table. We're not gonna use this in anything. Okay, and the prefix that we have calculating using the 24 network bits plus the subnetting bits is going to be attached to each subnetwork of each of these 8 subnets. So I'm just going to repeat this prefix all over the place. Okay, now if we have finished this main table, I think the only step left is to actually calculate the final IP address for each subnet of the 8 subnets. So let's take, for example, the first subnet that we have here. Alright, so the first subnet has the last octet of 8 bits to be all zeros, so the last octet is eventually just going to be 0. It's really obvious. And of course, don't forget the prefix, which is going to be //27. Let's go to the second subnet here. The second subnet has a 1 under the 32, so the last octet is going to be 32 plus the same prefix. And let's go to the third subnetwork here. The third subnetwork, you're gonna have 1 under 64, so you're just gonna have 64/27. And the fourth network, you're gonna have that the last octet actually is 96, which is 64 plus 32, 96/27. And the fifth one is going to be 1 to 8. I'm just gonna continue this. So this column is finished, and now we have the IP addresses of each one of our 8 subnets that we have just generated out of this IP address range. Okay, now after we knew that we have 8 subnets, the next thing to know is that how many IP address does each subnet has, or in other words, how many IP addresses can the subnet be able to provide to its hosts. So if you remember the host bits number, which is 5, we're just gonna plug it again in the same equation from earlier, which is 2 to the power of h minus 2. So we're gonna have, by the end of the day, 30 IP addresses. Alright, so each subnet of the 8 subnets is going to be able to cover 30 IPs or 30 hosts. Right now, regarding the -2 or the 2 IPs that's been deducted here, as I've told you earlier, this is the broadcast IP address that we're gonna see in a moment, and the second IP address that's being deducted is the subnet IP address itself, or the network ID. In this case, it is these 2 IP addresses, the subnet IP address, or sometimes it's called the network ID. These 2 IP addresses are not being provided to people or to clients to use. All right, it's reserved. We have successfully created our subnets. So if we created subnets in our VPC on AWS, we would want to predict what will the instance that we will create and locate inside that subnet. What would that instance's private IP address would be looking like? So we would just want to predict this by running quickly over the actual IP addresses range that can be generated from each subnetwork. Okay, so these 8 subnetworks, or these 8 subnets that we have created, I have listed them briefly here. I've just listed the first one, okay, which is the same one as this, and I have listed the second, the third, and up until the 8th subnet. Okay, so let's take the first subnet only and try to figure out the range of IP addresses that this subnet can actually generate, starting the first, the last, and the broadcast ID. Let's first determine the first IP address, since it's the easiest one. Now, the first IP address is going to be obviously starting at 1 here. Okay, so this is the first IP address that can be given to any PC, virtual machine, whatever, right? And let's go to the broadcast IP address, which one of the IP addresses that gets deducted whenever a subnetwork is created, and it doesn't get provided to clients or users. Okay, you can determine the broadcast IP address easily by looking at the next subnetwork IP address. Looking at the last octet, you see that you have 32 here. So obviously the broadcast of the previous subnetwork is going to be preceding this by 1. So we're gonna have the broadcast at an octet of 31, okay? And the one before it, just the one right before it, is the last IP address, which precedes it as well by 1. So we will have here 30. So we would have a range of IP addresses starting at 192.168.11, and this last octet will keep on increasing up until 30. So as per our calculation, we can see that actually, yeah, the subnetwork actually contains 30 IP addresses, starting this and ending with that one. And this is the broadcast. Okay, so these 2 IPs that being deducted are the broadcast IP address and the subnet, or the subnetwork IP address itself, which is this one, and sometimes it's called the network ID. Second design case that we're gonna have is basically the one that we're gonna implement on AWS. So I'm going to go to my console here, registered as an IAM user who has administrator privileges. This is the region that I am at. Notice the availability zone, it's US East 1. So I'm going to go to VPC. First we're gonna create our virtual private cloud, which is basically going to work as our main network, right, that we are going to create subnets out of it. It's the same thing as having this given IP address that we worked on. This was our main network, so consider something like this is going to be our VPC's IP address. Alright, so let's go there and VPCs and go to my VPCs. This region, I believe I have no VPCs created, so let's go to create VPC. By the way, you can create your VPC from the dashboard and the VPC wizard, but I'm just going to create it like this. Let's name it something meaningful to ours. I'm just going to name it CS, let's say CS class 2020 module. No, let's just name it CS class 2020. Okay, since I'm doing this for a class that I have. Alright, now if you noticed here, it's telling you that you should specify an IP version 4 address range as a classless inner domain or setter block in this category or in this field, and it's telling you that you can use this example for instance. Alright, if you looked here, you can see that the recommended IP address that you can work or start working from is 10.0.0.0 with the net masks starting from 24 or it's between 16 and 28, so you can pick whatever net mask or prefix that you would like to choose. Alright, and if you went to VPC subnets, you would see the same thing. Let me just navigate to it. You would see the same IP address or classless IP address being presented there for you as an example, and it's telling you that this is the primary setup block for VPC. So we might as well want to work on this IP address. So I'm going to paste it here. Now what is left is to pick our prefix or net mask. I personally will go with 24 since I need a couple of hosts, but I don't want to have a great number of host bits being wasted, so I just need 8 bits for the host. I think this will do the trick for me. Notice that this design case that I'm taking you through, which is my actual personal design case that I have implemented, I need PCs or IP addresses for 120 members or 120 students. Alright, so I guess picking a prefix of 24 bits for the network and leaving 8 for the host, I think this is gonna work for me. You can pick, as you see here from the recommended net masks or prefixes, you can pick between 16 to 28, so it's up to you really. Alright, I'm gonna pick the first one, which is /24. Okay, so this is our main IP address ranges. This is the main network that we're gonna create subnetworks of. I'm gonna leave the default stuff here as it is. I don't need an IPv6, but if you needed one, I think you can provide it. Let's click on create. Now we have created our VPC. Let's take a look at it. It's there, right? It's called CS class 2020. Now if you take a look at the description here, you're gonna see that this is the IP address version for setup blocks. This is the IP address range. This is the IP address of the VPC itself. Alright, we haven't created subnetworks yet, so we're gonna create subnetworks of this VPC right in a moment, just when we actually do it by hand first. Alright, so notice this is the VPC's VPC's IP address range that we're gonna work on. So let's take this design case now. It's a group of 120 students or members. Each one should have his own PC and IP address. Let's take the same approach. Now looking at the traditional classes, you can tell that class C gives you the least number of host bits, which is 8 bits, right? If you took this and plug it in the formula, which is 2 to the power of h, which is the host bits, minus 2, which is the broadcast and the subnet IP address or the network ID, you're gonna have 2 to the power of 8 minus 2, which is 254. It's the same thing. This is the total number of hosts if we used an host bits of 8 bits. Now the number of wasted IPs is going to be 254 minus the actual number that we need, which is 120 IP addresses. You're gonna be wasting 122 IP addresses. So instead we're gonna pick from the right side geometric sequence that we have, which follows the formula 2 to the power of n, the number that covers at least 120 IP addresses, by just tweaking the equation here, this one, and replacing the equal sign with a greater than or equal sign, and this is the variable that we want to actually achieve. So if you look there, the power that you can use as the host bits that will cover at least 120 IP addresses is going to be 128. Alright, so we're gonna use the host bits as 7 bits. Okay, this is the coverage that we need here. Anything less or anything more wouldn't work for us. So let's just substitute this. 128 minus 2, this is gonna leave you with 126. Okay, so each subnet that we will create will contain 126 IP addresses. Okay, so there can be 126 hosts in each subnet. Now, how many subnets will we have now? We don't know yet. We will know this shortly when we know how many subnetting bits do we have. Okay, so let's substitute this, and this is the number of host bits that we can use to begin our subnetting over this IP address ranges, or the VPC's address. Okay, now we will do the same trick here. I have a prefix of 24 bits for the network, so the first 3 octets, as you can see here, are reserved for the network, which we cannot modify. So we can only play with the last octet there, which is 8 bits. That I have done the same thing as before, and I have listed them in 8 columns. As you can see, this is bit 1, bit 2, bit 3, bit 8, and the first bit that we have here follows the same geometric sequence: 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, until 2 to the power of 7, which is 128. Alright, and this is the prefix that we have chosen for our VPC, and I have just put that prefix there, which is eventually going to change when we add up the subnetting bits that we will configure to the rest of the network bits. Okay, so the network length or the prefixes will eventually going to be changed. Now, let's first substitute the 7 first bits of this octet that we are working on here to be host bits. Okay, so I'm just going to fill them. Alright, so the first 7 bits are the host bits, which leaves us with the last bit here, which is eventually going to be the subnetting bits. Okay, so once we determine the number of subnetting bits, which is in this case 1, we can determine the number of subnets that we will actually create out of this IP address ranges of the VPC. Now, due to the power of s, if we plugged s with 1, we will find ourselves left with only 2 subnets that we can create. So from this VPC's IP address, we can create 2 subnetworks, right? Okay, so since we know that we have 2 subnets or 2 subnetworks, I'm just going to add 2 rows. Okay, I'm just going to copy this. So I'm just gonna pause the video. Okay, so regarding the 2 subnets that we have determined that we will actually achieve, I've created 2 rows, each one for each subnet. Now let's fill up the mini table of the subnetting column here, which is basically going to be only 0 and 1. Remember that the first column of the subnetting bits is going to follow the first term of the geometric sequence, which is 2 to the power of 0, which is 1 for each binary digit. So 1 0 and 1 1. Okay, now after we finish this table, the thing is left for us is basically to substitute the subnetting bits with zeros, assign them for with zeros for each row or each subnet. Okay, I'm just gonna copy this like that. Okay, and now we would want to determine the new prefix or the new network length. Notice that this IP address used a network length of 24. Okay, 24 network bits. Now we have 24 network bits and we have 1 subnetting bits, so the total network length is going to be 25. So this is the new prefix that these IP addresses will have. Okay, now let us finally evaluate the 2 subnets IP addresses. So the first subnet IP address will going to be the last octet will be only 0, so it's going to be eventually 0 with the prefix that we have just calculated, and the second one will have a 1 under the 128, so the last octet will have 128 there with the prefix. Okay, so these are my 2 subnets. As I told you, we have two subnets. To determine the number of IP addresses each subnet will contain, we will just use the previous formula and say 2 to the power of h, which is the host bits, which is 7, which gives you 126 IP addresses in each of these subnetworks. Okay, this is just for us to understand what will actually be our private IP addresses that our instances will be assigned, and to make sure that our hand calculations are actually correct and following the pattern that we have just been doing all along. So let's take, we have only two subnets. This is the first one and this is the second. These are the same ones here and there. So let's take the first one, for example. If you want to get the first IP, it's as easy as just putting one at the last octet, and the broadcast IP address will be the one preceding the next subnet IP address or the next subnet network ID, okay, which is in this case 128, so this is going to be 127. The last IP address will be the one preceding the broadcast IP address, which is going to be 126. Okay, so you can tell that the range of IP addresses that can be generated in this subnetwork is 1 to 126, so we have a total of 126 IP addresses. If we looked at the second one, the first IP address will be the one right after the network ID, which is 129. The last IP address is going to be 254, and the broadcast IP address will be the last IP address there, which is 255. Okay, so it's time to create our subnetworks. So I'm just going to create these subnetworks in AWS console. I'm just going to go to the subnets there, and these are previous subnets that I have already made, or I think these are the default ones. I've created another subnets and VPCs in my other region here in Oregon. So let's create a subnet and let's name this, for example, CS Class 2020, and it's a good idea to prefix your subnet's name tag with the availability zone. So let's say that my availability zone is at US East 1A or US East 1, as you can see here. So I'm gonna make two subnets, and I'm going to make all of these subnets public, and I will tell you what do I mean by public. Okay, so let's attach, I'm gonna pick this one, okay, 1A. So I'm just gonna attach 1A to my subnet tag, just to know that this subnet corresponds to this availability zone, and we will pick the VPC that we have just created. So this means that the subnet we are creating is following under this main network, right, which we give the address of, as you can see, 10.0.0/24. Now that's the most important part here, which was the reason of doing this subnetting tutorial, is actually determining the subnet IP address. Okay, so the subnet's IP address can be one of these two. One of these two. We have created two subnet addresses, so let's pick like one of them. Eventually we're going to make two subnets, so we will be substituting both of them anyway. So I'm just going to pick the first one. I'm going to paste it here. Okay, notice that if the subnetwork IP address version 4 or setter block was incorrect, you're gonna get a message from AWS console telling you that this subnetwork IP address isn't really correct. Okay, so let's create the first subnetwork. Let's go to the subnets in the dashboard, and you can see this is here. This is the first subnet. Let's create another one. Create subnet. Let's do the same convention with the naming, public. I'm just going to leave this like this. So let's say that this is a private one, okay? And I'm going to tell you the difference. And let's pick this to be in the availability zone, or you know what, let's just make them both public, but I will tell you the difference between a public and a private just in a moment. Okay, so let's pick the second availability zone, which is 1B, for example. So this is going to be 1B here. The first one was 1A, this is 1B. Okay, so this will be under the same VPC that we have created earlier, which follows this IP address. Now the IP address of the subnet is gonna be the second IP address that we have created here. Okay, now let's create the subnet. Let's view our subnets. We have now two subnets. We have the public 1B. Maybe I just want the naming to be the same here, so I'm just going to stick with this convention. Okay, so we have two public subnets. One follows the zone of 1B and the second follows the zone of US 1A. Okay, if we looked at one of them, let's take the first subnet for example and go to the description. You're gonna see that this is the subnet ID and this is the VPC, which is CS class 2020 that we have created, that has the IP address of 10.0.0.0/24, and it follows this availability zone. Okay, this is the IP address that we have given the subnet, the one that we have created here and there. This is the IP address of the second subnet, the ones that we have calculated earlier. This is the routing table. If we looked at the routes table here, we will see that if we expanded this, this is the route table that has been made by default for our VPC. If we took a look at this, you're gonna see that you only have local routing route. So the IP addresses that is of this range are the only IP addresses that can send and receive traffic within the network. Okay, this means any subnets from this IP address, any IP address from the subnets inside that or of that IP address will be able to send traffic and receive traffic inside, locally inside this VPC or inside this network. Okay, so this is the routing table. Shortly we will add an internet gateway to let our subnets be able to connect to the internet and send requests or send traffic outside the VPC's network, which is this one, and also receive traffic from the internet. Okay, if we looked at subnet associations, we're gonna see that this routing table is addressing the VPC, but we have not associated any subnets there. Okay, so we will do that shortly when we want to make them public. We would want also the subnet to have the ability to go to the internet. I will explain this shortly. Okay, so after having the subnets, let's now go and create our ACL. If you went to this one for example, you're gonna see that this is the network ACL. Okay, by default you get a rule that allow traffic from any IP address as an inbound rule. Inbound basically means that these are the traffic coming in into your subnet. It's coming in from outside, it's coming in from the internet, or it's coming in from another subnet for example. So this is what inbound means. So you are able to receive any request or traffic from outside of your subnet. This is what this IP address means. Okay, so any source, any IP address, any source can send you a traffic and enter your IP and enter your subnet. Okay, using any protocol, using any service type or application layer protocol like HTTP or HTTPS or SSH, with any range of ports. Everything is available. This is the default when you create any subnet. This is what AWS actually attach to your subnets. And the same goes for the outbound rules. Outbound rules mean that you are the one now sending from inside the network or the inside the sub network into the outside world or into the internet for example. So the outbound means that you send traffic from within the sub network into other sub networks in the same VPC or into the internet. And hence the meaning, this table says that you can send any traffic to any destination, which is these zeros actually mean. So you can send to any IP address any kind of traffic using any application layer protocol based on whatever transport layer protocol that you're gonna use, TCP or UDP, using all ports. Okay, so we're gonna modify this because this is not secure at all, so we would want to modify this. Before getting into the network ACL, I just want to let you know what is the difference between a network ACL and a security group. If you look at security here, you're gonna see a network ACL and the security group. This is the one made by default, the one that I was showing you earlier. This is the default inbound rules, and this is the outbound default rules that has been attached to our subnets that is following our VPC here. Okay, so we have two layers of security. We have the network ACL. ACL means access control list. The second one is the security groups. So what is the difference between the two of them? The security group is at the level of the instance, meaning that whenever you create a virtual machine, you would be given the option to set a security group, which is the second layer of defense. Okay, remember that an instance falls into the subnetwork. So whenever a traffic is coming to the subnetwork, the first thing that it's going to face is the defense layer, the first defense layer, which is the network ACL, the network access control list. Okay, so if it passed the ACL, it would go to the instance. It will try to communicate with the instance. The instance would have another layer of defense, which is the security group. If it passed the security group, then the traffic will reach the instance, whether it was SSH-ing into the instance or requesting a web page from the instance, stuff like that. Okay, so this is the first layer of defense, and this is the second layer of defense. The network access control lists are at the level of subnetworks. Okay, subnetworks can have one access control list, and if you created an access control list, you can attach it to multiple subnets. All right, but the security group is, as I told you, is at the level of the instance, and you can make a security group and attach it to an instance, and when you create another instance, that security group that you have created earlier is going to be saved, and you can attach it to the new instance that you will be making, and so on. Okay, so let's go to the network security group and let's modify our default ACL. I'm just going to give it a name. Let's call it CS Class 2020 ACL. Okay, now let's go to the inbound rules and let's edit these. I'm going to list to you the most important rules that you might want to have at your ACL, that you will eventually search the internet and maybe copy it from something like this. You're gonna find in the documentation some recommended inbound rules and some recommended outbound rules that you can give to your ACL. I'm just going to use the most important ones that you're gonna find in the documentation, and ones that I found myself personally needing, and I will explain them shortly to you. So let's take the first rule. The first rule obviously is going to be SSH, and we would want, of course, SSH is it's at the application layer, and it's carried on this transport layer protocol, which is the TCP. It's always by default on the port 22. So the only thing left for us is to modify the source. Remember, inbound means anyone from outside your subnetwork is trying to enter your subnetwork, then enter your instance or virtual machine. Okay, so at your case, you would want, for example, your PC, your local machine that you are working from right now, to be able to access your ACL, which is the subnetwork, then enter the instance itself, right? So your source could be your IP address, but I recommend to leave the source as 000. And okay, the whole point of having the source as 000, it means that any IP address can SSH to your machine. Or let me rephrase, any IP address can SSH into your subnetwork. Okay? This might be something that you don't want, as I said earlier. Maybe you would want to have your machine's IP address in this source, but this will come later at the layer of defense of the instance itself. See, it makes sense if you put your IP address over the instance itself. So let's say that there is some kind of machine that tried to SSH into your subnet and it entered the subnet. That's fine. But whenever it tries to enter the instance inside the subnet, of course the instance would have an SSH rule just like this, but with a source of your own IP address. So any other IP address entering the instance at the security group security level will not be allowed to enter. There is another reason for me leaving this at all zeros. Notice earlier when I told you that ACL or access control lists can be attached to multiple subnets. Now, if you're attaching these rules that we are going to populate just in a minute to multiple subnets, you would want them to be as general as possible, meaning that they can work for any subnet. Okay, so imagine you put your IP address there at the source instead of all zeros, and you attached this ACL that we are creating, which we named CS class ACL, to another subnet. Okay, you have created another subnet and you have attached this ACL to it, and all of these subnets will be having an ACL that has a rule of an SSH which only allows one single IP address to enter them, which is your machine. Imagine how many subnets can be actually inconfigurable because of a move like this, and so many people would be trying to SSH into their subnets and they wouldn't be able because their IP addresses aren't the one listed in the source. And instead you have listed your own one and just distributed this ACL to everyone. Okay, so leaving the SSH rule in the ACL to be all zeros, to be accepted from any IP address, is a good move. Whenever we come to the security group at the layer of the instance itself, that will be the time when we actually put our own IP address on the instance. So we'd be the only ones who can SSH into it, or actually any other IP. We can put custom IPs there. So let's add another rule. Let's call this 110. There is a naming convention for the rule to have a step of maybe 10 or a step of hundreds. It's up to you. Okay, so let's pick the second one, which is the HTTP protocol. It's by default in port 80. The same thing applies, the same concept that I have just explained to you regarding the SSH, letting anyone SSH into the subnetwork, is going to apply at this HTTP rule as well, because remember, this ACL can be attached to multiple subnetworks, so we would want it to be as general and working for everyone. All right, so let's add a second rule, which is going to be HTTPS. Okay, it's by default in the port of 443. Now I'll add the ICMP version 4, IP address version 4. What does the ICMP do is basically it gives you the ability to ping. If you are familiar with these utilities, it lets you ping and communicate with other websites or web servers. Okay, and it lets you also download stuff from other websites. Let's say GitHub, you're cloning something or you're downloading something. If it didn't work, try to ping. If it didn't work too, then this means you need the ICMP protocol there. And since I don't have anything related to IB version 6, I'm just going to include the IB version 4 type of ICMP. Let's give this rule as 130. Okay, so this protocol is what's going to let you communicate with other websites or with other IP addresses, if you may say. We will leave the source to be all zeros, meaning that any website can communicate with us, can ping to our IP address, or can send us traffic. The last rule in the inbound rules that I would like to add is a custom TCP rule, and I will give it this range of ports. Alright, what does this mean is essentially, say that we have sent some request, we have sent some traffic to an IP address that is outside of our subnet, alright, requesting some kind of resource. So the request or the traffic that we are sending outside to the outside of our subnet to that IP to that specific IP address is originating from our subnet, right? Eventually, if we're sending this kind of request, the web server that we are communicating, or the IP address that we are communicating with, would like to respond to us, right? So it will send an incoming traffic, it will send an incoming return traffic, right? If we didn't allow this custom TCP rule to be able to accept traffic from this wide variety of ports, we may not be able to receive the response coming out or coming in from that IP address that we have initiated the communication with. Alright, so just think of this custom TCP rule as requesting something from some website. Alright, actually the requesting part is going to be the custom TCP rule in the outbounds. Alright, I'm going to talk this in a minute when we get to the outbound rules. So we have requested some web page, something from outside of our subnet, and the response from that external IP address that is not in our subnet is using a different protocol than the ones listed in our inbound rules. It may be using a protocol that we have not listed here. It may be using an application layer protocol, a network layer protocol. Bottom line, the response or the return traffic may be using another type of protocol that we have not listed in our rules, with a different configured port number that we also have not listed in our rules. So in order to receive that response, no matter what TCP protocol it is using and no matter what port is using to communicate with us and send traffic, we would like to accept it. Okay, this is essentially the meaning of having a custom TCP rule in our inbound rules. And this is the inbound rules. I think this is the most important rules that you might need. Okay, so let's save this. And now let's go to the outbound rules of the ACL. See, we have updated the inbound rules. Notice that the ACL is attached to both subnets. So both subnets has inbound rules of these rules. Okay, now let's go to the outbound and see what we'll do. Outbound means that you would want to send a request out of your subnet. Alright, so maybe you would want to send an HTTP request or an HTTP kind of traffic. Okay, we will leave the destination zeros as well, because you might want to send to any IP address as a destination. Let's add another rule. The same applies for HTTPS. Let's add another rule. Oops. The same thing goes with the ICMP. Say you use the ICMP in the inbound rules in order to receive traffic coming or receive returning traffic, if you may say. Okay, you would want to be able to send traffic. If you have the ICMP in the outbound rules, this is the one rule at the outbound is going to let you ping to other websites. Okay, so being able to ping to other websites or send the traffic to request some download files or some files that you would want to download from website, this means that you should have the ICMP at your outbound, since you are sending traffic into other websites that you would want to communicate with or have files from and stuff like that. Having the ICMP, on the other hand, on the inbound rules actually relates to the returning traffic. Say in the outbound you have sent a request to download, for example, a distribution from GitHub, okay, but you never received a reply. Not receiving a reply is because you haven't included the ICMP in the inbound rules. Okay, but if you saw something returning and the files are starting actually to get downloaded, this means that you have included the ICMP at the inbound rules. Okay, so including the ICMP in the inbound rules just allow the returning traffic to come back to you. Okay, we would want to have the same custom TCP rule here. Okay, let's have this for example case here where you are hosting your website on the subnet. Okay, so you are hosting your website in the subnet that you have created. Okay, and there are clients of different IP addresses that is out of your subnet trying to request pages. They are trying to click on links and visit routes on your website, which is included in your subnet, and they are requesting pages. So you would want to respond to them with the pages that they need from within your subnet to their IP addresses. Okay, this is why we are including the custom TCP rule at the outbound, because we are sending the traffic or the responses, for example serving web pages and stuff, to other clients who are requesting them. Okay, and the same thing goes with the number of ports. We're gonna have the largest number of ports that we can include. Okay, and we would want to have the destination to be any IP address, meaning that we can send responses to any IP address. Okay, so hope this is clear to you. Now let's save this, and we can say now that the ACL is ready. Everything is set regarding the inbound and the outbound. Alright, the only thing left for us is now to create an internet gateway to actually make the subnets that we have created here public, as the name says. Okay, by default all of the subnets are private. Alright, and private basically means that they cannot communicate with anyone outside of the IP address of this range. Alright, or let's say outside of the IP address of the VPC's range. Maybe they can communicate with an instance on a private subnet can communicate with another instance on a private subnet, but whenever this instance that's going to be located in this subnet, for example, tries to communicate with a machine or an IP address that is outside of the subnet and outside of the VPC on the internet, this is not going to be possible because this is a private subnet by default. So how can you make this public? First of all, we need to make the VPC itself, the main network that contains the subnet, be able to connect to the internet, be able to send traffic and receive traffic from the internet, and this is by creating an internet gateway. Okay, so we have a default internet gateway, which is not associated with the VPC that we have created. So let's create an internet gateway. Let's call it I'm just going to name it anything, CS, for example, CS class 2020 internet gateway. Alright, let's add the W here. So let's create the internet gateway, and you can see that the internet gateway has been created. Alright, but it's not attached to anything, meaning that it is not associated with any VPC yet. So let's attach it to the main network of ours, which is the VPC's IP address range. Right, so let's just click on actions, then attach to VPC, and let's pick the VPC that is on our region. In my case, I only have this VPC that I have just created with you. Let's attach the internet gateway, and now the VPC will be able to connect to the internet. If we went to the VPC, you would see that if you went to the routing table, and went to the routing table of the VPC, you would see that there is only one route. Okay, there is only one route in this routing table, meaning that any IP address in this range of IP address, any IP address in this VPC or in the subnets of this VPC are the ones that can actually send and receive traffic locally within, as you can see here, internally within the subnet or within the VPC. Now, since we have an internet gateway attached, we can add another entry here that says that we can send traffic to any destination on the internet. Okay, not only sending traffic to any IP address of this range locally within our subnet. So let's go to edit routes and add route, and let's pick the default, which is 0000/0. Okay, this means that we can send traffic to any IP address. Alright, but the target is the most important thing. We're gonna choose the internet gateway, and now we're gonna find the internet gateway that we have created earlier. So we're just gonna pick this, and this means now that we can send traffic to the internet at any IP address out of this range of our VPCs and subnets IP addresses. via the internet gateway. Okay, so let's just save the rules. All right, now if you looked at the routing table, I'm just gonna name this CS class 2020 routing table. Okay, so this is our routing table. It has now two routes. The local one, which means that any IP address can connect or communicate with any IP address within the range of IP addresses given by the subnet of this VPC. And as I told you, you can now send traffic to the internet to any IP address out of this range. If you looked at subnet association, you would see that there are no subnet association yet, meaning that the subnets are still private. Now let me just try to explain this to you as easy as possible. Think of it as a passenger who has a plane ticket, and he needs to go through two confirmation steps in order to get to the plane. Okay, the passenger in our example is traffic that we are trying to send from within our subnet. See, the small bubble is the subnet. The bigger bubble that contains the smaller one is the VPC. Okay, and the greater bubble is the internet. Right? So the passenger in our case, or the ticket, the plane ticket here, is the traffic that we are trying to send from our subnet to the internet. Notice that the traffic within our instance inside our subnet is trying first to pass the first confirmation level, which is going to be the subnets level. So it needs to bypass the subnet in order to get to the internet gateway on the VPC's level, or on the VPC's edge to get to the internet. Okay, so for the instance to be able to send traffic, it needs to go to the subnet. It will not bypass the subnet if the subnet was private. That's why we need to make the subnet public. We need to associate it with the same internet gateway as the VPC, so to make it public and let the traffic, if it wants to go to the internet, get to bypass the subnet level. Okay, since it's now public and it's associated with an internet gateway, and go to the next confirmation level and bypass the internet gateway on the VPC's edge and go to the internet, now to the specified destination. Okay, so in order to make our subnets public, we're just gonna click on edit subnets, and you're gonna see here that these are the two subnets that we have created regarding the two availability zones. I'm gonna pick both of them to make them public. And now we have two public subnets that are associated with our internet gateway. Okay, now this is almost everything we need to do. The only thing left now is to create our instance and locate it within the VPC within the subnet. So let's go to the EC2 dashboard. Go to the running instances. I don't have any running instances. I haven't initiated any of them in this region that I'm in right now. Go to the launch instance button and pick the AMI that you would want to boot the instance with. I'm just going to go with the first one, Amazon Linux 2. And this is the free tier eligible instance type, which is the T2 micro. It comes with one virtual core and it comes with one memory of RAM. I think this is going to do the trick for us, so let's go to the next configure the instance details, and this is the most important part. Now specify here how many number of instances that you want to launch. I want to launch only one. If you wanted spot instances, you can request that. And here is our main work. Let's pick the network that we would want this instance to be located at, and remember, this is the bigger bubble, which is the VPC. Okay, we created the CS class 2020. Now pick the subnet that you would want to choose. All right, so we have created two subnets regarding these two zones here. All right, so I'm just gonna pick the second one, which is the 1B, CS class 2020 public 1B. Okay, now if you want to auto assign the instance a public IP, then go ahead and do this. I'm going to enable this option. This is going to be useful for you if you wanted, like for example, to run some web server on this instance. You would want to need the IP version 4 of that instance. Okay, I'm going to leave everything else as default, and I'm going to click to storage, and this one is what I was speaking about at the beginning of this video. here, creating the instance beforehand, we get to actually configure the size of the storage or the AWS volume that we want to have. You can add multiple volumes. Of course, the whole reason of me creating a Cloud9 SSH environment was to reduce the number of GBs considering the size of the volume. See, by default, when I discussed this with you at the beginning, when you create a Cloud9 environment using the first option, will induce you to create an instance in order to create the environment. It will get you a default ABS size of 10 GBs. Now we can reduce this here. As you can see, I have created multiple instances before, so that's why I have 8 here, and by default this is the least number. If you try to click next, it's gonna tell you that regarding the GB2, you can only have the minimum size to be 8 GBs. By default, if this is the first time you create an instance, I think you'd see something like this. You'd see that you have a size of 10. Alright. There is another important thing here. There is the provisioned IOPS SSD or IO1. This type of volumes is really good regarding the multi-sharing. Search for the multi-share feature in this volume type, IO1. Multi-share basically means that this volume can be attached to multiple instances, meaning that you can have one volume shared with, let's say, 3 or 4 instances. This might be good if you were considered about the size of the ABS volume, but remember, this will cost more money. This is out of the free tier eligible, so I'm just gonna stick with the GB2. I'm gonna click next. If you wanted to add some tags, you can go ahead and do that. I'm not going to do this here. Let's go to the security group, and remember the 2 security levels that I was talking to you about. The first one was the first defense layer or the firewall of the subnet, which is the ACL that we have actually created, and we made it as general as possible in order for it to work as a template for as many subnets as we can, or as many subnets that we want to attach that ACL to. Right now, here comes the customization for your own instance. So this security group is the layer or the defense layer of the instance itself. So let's say that we have created this instance to be located in the subnet that has a general template of an ACL, which, if you remember in the inbound rules, it has an SSH rule that accepts incoming traffic or incoming SSH connecting or connection from any IP address. Hence the source were all zeros. Alright, this where customization for the instance itself comes handy. Now we would create a security group for this instance. If you have created previous security groups, you can select an existing one, but I'm gonna create one with you. I'm just gonna call this web access, let's call it CS class, just to identify it. Okay, so this is the name of the security group. I'm just going to repeat this in the description. Alright, now what you really would care about, or me personally, what I really would care about when I'm customizing the rules regarding the inbound rules for the instance that I am willing to connect to, is to be having an SSH rule that only me who can actually connect to it. Okay, I hope the image is clear now. We created a template, an ACL template, and we attached it to the subnet with an SSH of all zeros, meaning that anyone can connect to the subnet. But whenever someone can get to the lowest layer, which is the instance, is lying in that subnet and wants to connect to that subnet, he wouldn't be able to connect to that subnet via SSH if his machine or her machine wasn't listed in the security group, which is the defense layer of that subnet, of that instance itself. Okay, so if you wanted to have custom IPs, and we're gonna do that shortly when we connect our Cloud9 via SSH, you can list multiple IPs here. Maybe you I'm sorry, maybe you have a machine that has this IP address, and I have another machine that have another IP address that you would want it also to be able to connect to this instance via SSH. So you can add custom IPs in this using this option here. I'm just gonna go with my IP. All right, and let's review and launch. Everything looks good. Let's launch this now. If you would want to connect to this via SSH, you would want to choose a key, whether it's an existing key. In my case, I haven't created any keys in this region, so I'm going to create a new key bearer, and I'm just gonna call it CS class key 1. Notice that the auto assign IP address that we have enabled when we were configuring the instance earlier in step 3 here, this auto assign public IP will give the instance a specific IP version 4 address for the time that it is running. Whenever you stop the instance, the IP address that has been auto assigned to the instance will change whenever you run it again. Okay, so if you're SSHing and you have stopped the instance and you try to run it again and SSH to it one more time, you would need, using the same key, by the way, using the same key bearer, you would need to update the host. Alright, which is in this case the newly auto-assigned public IP address. If you don't want to have a dynamic auto-assign IP address every time you stop the instance and you run it, then you should go for something called the elastic IPs. An elastic IP is basically a static IP that you enable and attach to the instance of yours. The only catch here is that an elastic IP will cost you or charge you money if it is not attached to an instance. So just make sure that once you create an elastic IP, attach it immediately to the instance. Alright? The couple of seconds or couple of moments before you attach it to an instance would cost you money. So just bear that in mind. Alright? I'm just going to download this key bearer. Okay? Notice that it downloads in a PIM format. So if you're on Windows like my case and you want to connect to this instance via SSH, you would probably use either PowerShell or Putty, and Putty is the software that I'm going to use. The problem with Putty is that it needs a pair or a key bearer of the format PBK, not PIM. So we're just going to convert that to PBK when we get to that point. Okay, so let's launch the instance. Let's go to the instance and view them. We have this instance. It's gonna take some time until it initializes and launches. Okay, so the instance is now running. It's just gonna take some time to initialize, and it's gonna give you 2 out of 2 status checks if everything went smoothly. Let's just name this instance and call it let's call it CS class let's call it CS class 2020. That's it. Let's just call it this. Okay, so let's have a look at our instance here. This is the instance ID, the instance type, the availability zone, and we don't have a public DNS. If you wanted to have a public DNS hostname, maybe you would want to use this if you are hosting some kind of web server or proxy server or whatever kind of server on your instance. You would want to have a public DNS. This is the auto assigned public IP. We didn't assign any IP version 6 IP addresses. This is the key bearer that we have downloaded that will we use shortly to SSH into our instance. And this is the security group that we have created, which we called Web Access CS class. If we went to this, you would see that this security group have the inbound rule of an SSH, which contains in the source our IP address. So my machine in this case is the only machine that can connect to this instance via SSH. Okay, and let's go back to the instances. If we look down here, see the checks is now ready. If we look down here, we're gonna see the most important part, which I was actually doing the handwriting or hand solution on the subnetting tutorial, so we can predict this. See, we predicted if we created an instance and made it fall into this subnet, just as we created that instance right here, it would eventually be taking an IP address starting from either 129 up until any range of addresses till you reach 10.0.0.254. If you looked at the private IP address being located to our instance, you're gonna find it having 200.238. Okay, so our predictions, our hand calculations were actually correct. This 238 falls in the range between 129 and 254. It falls in between there. So this gives you a solid idea about what you are dealing with and how can you predict the instances with their private IP addresses that you're gonna create. I think this just gives you a good background about how everything works. Okay. This is located in this subnet, which is public I1B. This is the second subnet that we created. All right, it's located in the main network, which is this VPC's ID, CS class 2020. And I think that's what you need to know. This is the security group attached to it. You can view the inbound and the outbound. I've just included the inbound. I don't need currently the outbound and anything. So this is your machine. Now let's try to connect to this instance via SSH since it's running. I have downloaded Putty. Okay, what you would want to do is first open up Putty generation, which you can generate the BPK out of this PIM format of this key, so you can use it afterwards. But if you didn't find Putty gen when you search for Putty like this, I think that you're gonna find only Putty. You can click on this start menu and you're gonna see Putty gen there. All right, so let's go and open up Putty gen. And I'm just going to relocate this downloaded PIM key so I can find it easily. I'm just gonna locate it here. It's called CS class K1. So let's load that key from the directory that we have saved it in. Notice that when you load on or open the directory of yours, you're gonna find only the BPK keys. So you're gonna need to preview all files and you're gonna see the PIM key of yours here. Just open it, and now let's save it as a PPK key. I'm just gonna give it the same name. Alright, and save. Now the key is saved. Let's open up Putty and let's go to connection, SSH, and authentication, and browse for our BPK. This is the one that we have created. And before you open it, let's just go to session and make sure that the connection is SSH on the port 2. Let's add the host name or the IP address, which is the IP address version 4, the public auto assign IP address of this instance that we have created, which you can find it here. Notice that again, this is a dynamic IP address being assigned. So if this instance has been stopped and ran again, you're gonna see that this is going to change. So if this changed, that just create another session with the same key but with a different host name. So I'm just gonna paste this IP address here and create a session so we can next time we can just double click on it and just connect it right away without every time writing the host name if the instance was already running. So let's save this as CS class session 1, for example, and save. We can pick CS class session 1 from here, double click. It's gonna ask you, click yes, and you should look as the AC2/user. That's the default login username for every instance that's being made on AWS, unless you have changed the user. If you didn't, then this is the default one to go to. Alright, so let's just recap and see where are we in the content of this video. We have made the subnetting tutorial. We have finished creating the VPC, making the subnets and creating them as public. Internet gateways have been created, and we have SSH and connected to the instance. What's left for us is to configure that instance, or in other words, to set it up to be ready to host a Cloud9 environment. Okay, so as you can see from this note here, we can run sudo yum update, and this to update some necessary packages, as you can see here from the message. So just hit enter. then click yes. After the update finishes, we will start our journey in setting up the instance to be able to host the Cloud9 environment. So let's just go to the documentation here. If you went to the creating SSH environment page of AWS, you're gonna say that there is some prerequisites in order to set up a Cloud9 environment which will contain this SSH host requirement. Okay, so our host or instance should have a couple of stuff. First of all, it should of course it tells you that it should run a Linux image, and it should have a VPC, a subnet, and stuff like that. We have configured everything regarding this part. It needs to be it needs to have Python installed. If you clicked on Python version, you're gonna see that Python version 2.7 is installed. This is gonna be a little bit confusing if you're not understanding what's going on in the Cloud9 editor. So if you're in the Cloud9 IDE and you have made some Python script and you try to run it, if the IDE detected that you have Python file opened, it will set the runner on Python 3. So it's going to execute your file using Python 3, which is not going to work since you have only Python 2.7 installed. So it's a good idea to update your Python. So I'm just going to install Python. By the way, sudo yum is equivalent to sudo apt-get in Ubuntu. It's the same thing, but this is an Amazon Linux, so it uses yum install of apt-get. So sudo yum install Python 3 will get the job done for you. It's gonna install Python, the latest version, which I believe is going to install 3.6 or 3.7. Maybe let's just make sure about that because I'm curious. So it's going to show you that the version of Python installed is 2.7, but if you did Python 3 version, you're gonna see that you have 3.7. all right, now after installing Python, we should install Node.js. In order to install Node.js on an Amazon Linux, you can install it using so many methods. One of them is to use the Node version manager, which is the one method that I'm going to use. So let's go there to the Node.js sample and get the link to download NVM. You can download either with curl or wget. So I'm just going to get this link to download NVM or Node version manager, which is going to allow us to install Node.js on our machine. So let's paste this. It's done, but if you searched for the command, you wouldn't find it. So in order to find or let the command actually get activated on your machine, you should either reload the bash or C script, or you would close the connection, the SSH connection, and connect again. So I'm just going to reload it, the bash or C, and now you should see the command working. Okay, so if this works, let's just say npm install node. It's going to take some time. Now if we want to see what node version has been installed, I think it's still in here, but you can open up the node shell and write whatever you want to do. The same thing goes with Python. You can open up the shell here anywhere. And let me just remind you of the ICMP protocol that we have added as a rule in the inbound and the outbound of the ACL that we have attached to our instance, which contains the running instance that we are connecting to right now. So if we try to ping, for example, to google.com, see when I press enter, the ICMP on the outbound is going to send my request, all right? And eventually Google will ping back, will return the response to us, and this response or return traffic will come through the ICMP on the inbound rule, like this. I hope this is clear now. Okay, the same thing if you try to download any files or stuff from GitHub or whatever. All right, the second part after installing Node.js and Python would be to set the path directory of the existing instance server to be having the access permission to read and write. Meaning that Cloud9, whenever it boots up, if you looked at the right hand side, you're gonna see a tree of files, right? in the left hand side, you're going to see a tree of files or your workspaces, or the directories included in your workspace. You can set the main directory to your environment, which shows up on the left hand side of Cloud9, if you wanted to have a different directory there, for example. Okay, you can set this in the path environment. Whenever we get to the point when we create the Cloud9 environment, you're going to see something called, it's an optional field, by the way. It's called the environment path. If you wanted to set a specific directory to open up whenever Cloud9 opens up. Okay, but I'm not going to do that. The most important thing is that whatever that directory would be, we would want to give it access permissions to be able to read and write into files, meaning that we could be able to remove files, touch some files, and make directories and stuff like that. So I'm just going to copy this line here. I'm going to go here, and that's it. Now the last step of setting up the infrastructure to host a Cloud9 environment on your instance is to install the Cloud9 binary. So let's go to the Cloud9 installer here. Where is it? Yeah, there. The Cloud9 installer basically, just as the documentation say, is just a Linux shell that checks whether the server or the instance that's running an OS and architecture that actually supports Cloud9 environment being hosted and ran smoothly on the browser. So we need to install this, install and run this binary. So we need to install this installer. So we need to install it either with the curl command or the wget command. I'm just gonna pick the wget for this one. I don't know why, but it's gonna have this error message. It's gonna tell you to install the GCC first. All right. So we're gonna go here. You're gonna see that this in troubleshooting. Let's go to the install GCC. For Amazon Linux, you can install the GCC by the way. And for your information, the GCC is basically a short for GNU, C, and C++ compiler. C, the installer for it to get executed and installed, it needs a C and C++ compiler, which is in this case the GCC. You can install only the GCC as a utility, it's by itself. But here in this link, you're gonna install something called the development tools, which is especially for Amazon Linux. The development tools are basically they contain a couple of stuff. It's the software development tools. Okay, it contains text editor for your Linux machine. It contains Vim and Emacs. It contains the C and C++ compiler, which is the GCC. It contains a version control and a debugger. If you wanted to install only GCC, you can search for how you can do that. Alright, but I'm going to go with the development tools and install the whole package. On Ubuntu, you're gonna install something called the build essential. So let me take this link right here and go to the instance and just install the GCC first. Alright, if the GCC installer has finished installing, just pick one of these links to download now the Cloud9 installer and run it. Pick this link, for example, any one of them. It's basically no difference. So copy it there and let the Cloud9 installer get download and install in your machine. Once the AWS Cloud9 installer has finished downloading and installing, this leaves us with the last step here in the SSH settings and requirements for the host. I'm going to get to this, but not currently. Let's start creating our Cloud9 environment. And we are going to be stuck at some point. It's not going to connect for some reason, which will bring us back to this point. So I just want to take everything gradually. Let's go to the Cloud9 dashboard from the services. I might as well want to keep the VPC one opened at some place. Now I am in my AWS Cloud9 environments dashboard. I have one environment that I've created like previously. I don't remember when, but this was a long time ago. So let's create an environment. Let's go there and let's name it anything. I'm just gonna name it something relative to what I'm doing. So let's call it CS weekly module, for example 1501. Let's take this away from here. Alright, you can give it a description. Let's pick the second option, connect and run in a remote server. Now we need to provide the user, which is the login name that you used whenever you SSH into your instance, which is in this case we have used the default user, we didn't change anything, so it's going to be AC2 user. And the port, of course, this is going to be an SSH connection, so the port is 22. Now the host, which is the IP address of the instance, which is going to be available here in the services, EC2. I'm just going to go to the instance that we created and pick the public version 4 IP address. Alright, let's go there and paste this here. Okay, now we want to expand the settings. See this environment path? It's an optional field that you can fill. That's what I was talking to you about regarding whenever Cloud9 boots up, it opens up in the left hand side a directory, a home directory. You can set it to whatever your default directory to be via this environment path here, but I'm not going to do this. I think I would go to fill this optional path here, which is the Node.js binary path. You can just get the Node.js binary using nvm which node. So this is the path for the Node.js binary. We're just gonna take it and copy it there. Notice that I have used nvm which because we have downloaded Node via nvm. If you have installed Node in a different way without the need to use an nvm, I think which node is going to do the trick. However, this is the advanced setting, this is all about it. Now what's really important here, remember when we created the instance, we downloaded a key. That key was actually the SSH key, the SSH public key that we used, and generated a BB key from it in Putty, and we were able to connect to it via this Putty session, right? The same thing applies for this connection to be established, is that it's telling you that the environment itself has a public SSH key. Alright, and this key needs to be registered in the authorized keys to SSH to your instance. So the key that we have downloaded and we have used it in Putty here in order to connect to the instance is actually registered in a file called authorized keys in the SSH folder. Let's go to the SSH folder on our machine. Let's just open it so I can let you know what I'm talking about. Okay. This is the authorized keys file. Let's open it with nano, for example. You would see that inside the authorized keys script, I only have one SSH public key, which is the one that I've downloaded within the creation of this instance, and I have used afterwards to connect to this instance via Putty, via this Putty session. Okay. In the same script, we would want to have the SS key or the SSH key of the environment that would want to connect to our instance registered as well in the same script. So whenever the environment tries to connect to our instance via SSH, the instance would have the key or the SSH key of that environment registered and written here. So it will give the environment access to have control and connect over SSH. Okay, so bottom line, the environment has its own SSH key as well, just as the instance that we used in Putty to connect to it. So we need to copy this public key and paste it in the authorized keys in order for the environment to connect. Now let's just click on copy key, and you're gonna have this prompt telling you that the key was successfully copied. I'm going to go to I'm going to go to the nano editor and inside this script, and I'm just going to paste it, save, and get out. Okay, that's the only thing here. Now what is left for us is to just click next, and it should connect to our instance. As a matter of fact, it wouldn't be able to connect to our instance. I just want to show you the message that will come up here. It's telling you that AWS Cloud9 couldn't connect to SSH server on this instance IP address. The problem here, if we went back to our security group, remember the security group that we have set up for our instance? We call that security group, let's see, where is it? Yeah, it's called Web Access CS Class. Let me just give it a name here. Web Access CS Class. I'm just going to keep it the same. So I have just named the group security so we can recognize it right on the spot. Let's remember what we have done in the inbound rules. If you remember, in the inbound rules, I have gave an SSH rule with the source of my IP address, my machine's IP address. And I believe you have done the same thing if you're following the steps accordingly. The problem here is that the Cloud9 service, just like any other AWS service like Code Build, for example, has their own dedicated machines. It runs on an Amazon machine somewhere near the region that you have picked. Like, for example, I am in this region, which is in Virginia, which is the same region that we have located our subnet to be at, right? Hence the instance is in the subnet, which is in this region, right? So whenever we want to connect a Cloud9 environment to our instance using SSH, this Cloud9 environment is basically running on Amazon machines. And these machines or IP addresses are being distributed all over the regions. That's why you get served the Cloud9 environment, which is closest to this region of yours. Okay, so bottom line here, the environment that we are trying to get it run on our instance is basically coming from another Amazon machine, which has an IP address. The problem here is that the IP address of that environment is trying to connect to our instance in order to open up the environment for us, but it cannot get to the instance. It cannot get through the SSH connection rule that we have put in the security group. Now, why am I saying the security group, not the ACL? If you remember, that's because in the ACL, if we went to the subnet that has our instance, I think you know this already, the ACL has an SSH inbound rule of all zeros. So this means the environment, the Cloud9 environment IP address, tried to get through the subnet, and it did that successfully, but whenever it got to the instance in the lower level, it got stuck at the security level edge, where we have specified only our machine's IP address to be the only IP address who is able to SSH onto this instance. So in order to let this actually work and let the environment, the Cloud9 environment, be able to connect to our instance, we need to provide the IP addresses of the servers that run Cloud9 service in our inbound rule in the security group in order to let the SSH connection actually work. So the first thing to do is to get the IP address of the servers that host the Cloud9 service, which is in the same region that we are. Okay, so to do this, you can search for something called AWS IP address range. You're gonna find a file called IB ranges, and it's in JSON format. So we're gonna need to download this file first. So I'm just gonna copy this link address, and using wget, I'm just going to download it in my user directory. If you list the files now, we're gonna have this file. But we need as well some kind of a JSON processor in order to traverse and query stuff from that JSON file. Now, if you continue the documentation, you would find when we go to the Linux here, you would find that the examples are using a tool called JQ. Okay, so we can go to the JQ tool. All right, and it's telling you that it's a lightweight, flexible command line JSON processor. So to download JQ on our Linux machine, we just need to write sudo yum install JQ. And hit yes, and done. The GQ is now, it's recognizable by the terminal. Now let's go and continue the documentation here. So the first example here is listing the creation date. Here you can get the information for a specific region. All right. Here you can get all the IP addresses of all servers that are hosting all AWS services. This is the same command, but for version 6. Here you would want to get IP addresses version 4 of a specific service like Code Build or Cloud9 or whatever. What we really care for is this one, is getting the IP version 4 addresses for a specific service in a specific region. Alright, so let me just take this and let's go and hit the right click. I'm just going to configure this, delete the Cloud9, the Code Build, and add the Cloud9. And the region, in my case, it's the same, US East 1. Alright, it's in Virginia, US East 1. Check your region from this part. Alright, So let me just hit enter. Oops. There's a key at the beginning. Oh my god, this is getting annoying. So this will list the IP addresses of the servers that run the Cloud9 service in the region of US East 1, right? So we're gonna take these IP addresses and list them in the inbound rules of our instance security group. So I'm just going to edit the inbound rules. I'm going to let this, it's gonna be custom. This is my machine's IP address where I'm able to connect to the machine or the virtual machine or the instance via the SSH Putty session. I'm just gonna paste the Cloud9 IP addresses from there. This is the first and this is the second. Okay, and let's just save the rules. If we're done, we can go back to the interface of configure setting and let's try to connect the Cloud9 environment to our remote server once more. Let's click next step and it works. Alright, now let's create the environment. Everything is working successfully. Let's check, for example, that we have the owner permissions to create files and folders. Let's make something like mkdir testing, and the folder is created successfully. Let's open up that file and create a Python file, for example. Let's go there. Notice that this is our user directory, which has the IP ranges JSON file that we have downloaded via the terminal. Okay. Now let me open the test.py and notice that this is a Python file. It has the Python extension. So by default, if you went and tried to run this, of course it doesn't include anything, but the runner by default has Python 3. Okay. So if you try to run this file and you haven't updated Python to Python 3 in your machine whenever you were configuring the instance and setting it up for Cloud9 environments, it would try to run Python 3, try to run the script using Python 3, and it will fail. It's going to tell you bash command Python 3 is not recognized. So you would need to go manually to the runner and click Python 2 for this to work. So let's make sure that everything is working. Let's save and run this. We are running this with Python 3 and it works because we have updated Python to Python 3. Let me just address one last point. I'm going to go to my dashboard. This is the environment that we have connected to our instance via SSH. Okay, so whenever you come back and you want to open this environment, you would just click open IDE. Well, this will work in the case of that your environment was always running. I'm assuming that you are using the dynamic IP addressing that I've talked about earlier. Okay, you have used this auto assign IP version 4 IP addresses. So your host or your instance has a dynamic IP address. So as long as it runs, this open IDE button will actually take you to the instance. It will boot up the environment on the instance successfully via SSH. But if the environment, or I'm sorry, if the instance has been stopped and you ran it again, if you click on open IDE, it will never connect. Okay, that's because the instance has a dynamic IP. So in order to figure this out, you just click on edit on the environment, and you're gonna see here that this is the information initially that you have used in your first SSH connection. Notice that the host will change if the instance has stopped and ran again. So you would just need to go to the instance, copy the new auto assign IP version 4 IP address and just paste it here, save the changes, and try to open the editor one or the open IDE for this environment one more time, and it would work. To save your time from all of this, you can just assign to your instance an elastic IP address. This is a static IP address that will stay there as long as the instance either it's running or stopped or ran again. It will be the same. Only catch, as I told you, is that this elastic IP needs to be attached immediately to the instance when it's created. Thank you, and I hope that I gave you an extensive and a good overview. If you have any thoughts, please do not hesitate to share it with me in the comments. In the next video, I think I will try to set up the code server and host it on an AWS virtual machine or instance. Anyways, thank you guys, see you later.